Alright, so now we're going to be coding out these derived equations that we got from parts A and B of our problem, and we're going to be bringing in some values for our different our two different tanks. So first, we're going to start off importing whatever we need. The first one is going to be a solve function. And we basically need this to solve the differential equations at the end of our video. It's from SciPy integrate, port, I believe solve IVP. Okay. And now we're gonna import Jax numpy as JNP. This gives us just a number of different functions. I believe most importantly for this one we need Jax numpy array. Or Jax. And then now we're gonna do some work with plotting our end result. So we're gonna need a few different things, starting with the plotly subplots. This will allow us to get subplots, and then we need to import some graph objects. There it is, makes it easy. As GO, or graph objects, just to shorten it. And then we need plotly IO as PO. And then since we are using the dark version or the dark setting on Collaboratory, just so it looks better, we're gonna make our graphs fit the color scheme, so it's not a blinding white. And I believe that's just plotly dark here. SciPy integrate import. Oh, wait. I did do that. That's weird. I don't remember deleting that. Solve IVP. That's weird. Okay. So now we're gonna look at the different constants for this problem. In the previous video, I explained, I laid out the equations, and we talked about the fact that we'll need radius, we'll need different heights, areas of the pipe, as well as cross-sectional areas. So we're given values for those, or for a few of those. Some we need to figure out. So we're going to start off with the radius of tank 1, which is 4 meters. Radius of tank 2 is 2 meters. Okay. So we have the area of the pipe, right? So from tank 1 to tank 2, that's connected via pipe, and that's 0.2, I believe. And the same area for the pipe leaving tank 2. And then now we need a initial liquid height, in the tanks. So do H1I, or height of tank 1 initial. And that looks kind of weird, so I'm going to separate it. I believe first tank we have value of 5 meters, and a second tank we have our value of 3. So, and then that's all we're given, or that's what we're given in the problem as far as constant values. So, we can also just throw our acceleration due to gravity, 9.81 meters per second squared, and just go and set that up. Okay. So now that we have that, we're going to start off with solving for the initial flow rates. And so I derived equations for this, I believe, in the first part of the video at a steady state. I talked about, I showed you what they would be, right? So it's Q1, 2, so the flow rate between pipes 1 and 2 initially, right, at a steady state, because we're assuming that our problem starts at a steady state, and then our flow rate at from in pipe 2, right, from tank 2 out. These are the two that we're going to be solving for here. So, but actually, with these values, geez, with these values above, we are actually able to get the value, and we could do this manually, but just to refresh your memory, as well as just to have it here in case values change, which I think is probably most important, because you're never given these exact values. But we're gonna basically just import these variables in and replace them for what we solved for in the first video, right? So start off with the area. It's right. Flow rate is cross-sectional area times the velocity of the liquid, and we solve for both. So first one's going to be A12. Then we have the JNP sign function, which basically just takes the sign between H1I minus H2I. And I messed that first one up too. And so this basically just gets assigned. Basically, if H2 at any point is higher than H1, it'll make sure to flip the sign and make it negative. So then we take the square root, so JNP, square root function of 2 times G times JNP, the absolute value of H1I minus H2I. Okay, and looks like I got past the first part. I was just checking to make sure I didn't make any obvious typos. Okay, our second equation is a little bit easier. We just take the area of the second pipe, and we multiply that by the square root of, it's just 2 times G times, it's just the initial height of the second one, which we have H2, H2I. And then we solved for our relationship of the inputs of that, right? So if you imagine it as steady state, the input has to equal the output. So for our first one, our Q1 in, and this is our initial Q1 in because it will change. So our Q1 in initial, that is equal to the Q12 initial, right? Because Q1 in, the only exit for our first tank is that pipe between 1 and 2. So Q1 in initial has to equal Q12 initial, right? Okay. And then our Q2 in initial has to be um, equal to the Q2 Q2. Do I have Q2 initial? I do, yeah. Q2 initial. Why isn't it? Oh, because I haven't shipped entered yet. It's a Q2 initial minus the flow rate between 1 and 2 initial. Okay. Let me run everything again. Okay. Before we move on, we can actually solve, or not solve, but look at these different values. So I just go Q12 initial and shift enter that. Yeah. So we know we're getting actual values. It is hard to, I know from repeating this a few times that is supposed to be correct. Let me try one of the initial ones down here. Yeah, okay. So we seem to be in good shape. So now what we need to do is actually get a function for our cross-sectional area, right? AC. So our AC function, which we derived at the very end, I believe, of the last video, is, or not, no, that would have been the first video. But I'll refresh your memory here. All we need is our H, our height of our liquid, and R. And then it is simply, I believe, pi, and then R squared, but R is R squared minus R minus H squared. Believe that's right. Well, we'll find out later. No, that's correct. I'm pretty sure it is. And okay, so now we actually can look at our change in liquid height over time. And this takes into account both flow rate, pretty much every flow rate, to account for this change over time, right? It actually needs to, because we're looking at the change in height over time in both tanks. So it's dH dt, right? Change in height over time. And then we need time and height. Okay. And now for our height, since we're working with arrays now, can just make, and since indexing starts at 0, our first height value is just going to be h0, and our second height value is just going to be h of 1. So yeah, that basically accounts for Python indexing and how it starts at 0. Now we're going to basically take these equations from up here, this Q12 initial and Q2 initial, but we're not solving for the initial, right? We're solving for the actual Q12 and Q2. So Q12, I'm basically just gonna, actually it might be easier, since, and this is a benefit you can actually do with, since I'm keeping my variables well named, in this case we can kind of just cut off every initial value, right, and change it to what will be the resulting or value at a given time, right? So I think all we needed to do was take off the h1 and h2 initial because that value is an unknown variable once we're not looking at steady state, because at this point we are no longer looking at steady state. We're just starting at steady state, and that's where we started, and now we're beginning to look at how our flow rates are changing with that height and over time. Same thing for Q2. This is Q2 initial. We can just take this down, basically just take that away. And now we're returning, and I'm going to need some space for this one actually. We're returning an array, so jax numpy dot array. Okay. So we start with our Q1 in. Basically our Q1, 2 and our Q2 are able to be solved, or no, sorry, our change in height over time. We actually ended up with our DHDT equations at the end of the last video. That's what we did. And we basically found it to be the flow rate over the cross-sectional area. So we have our Q1 in with respect to time minus our Q12, and that is over our cross-sectional area 1, and then next we're solving for second flow rate, right? So Q2 in with respect to time plus Q12 minus Q2. And that is divided by the second AC2. AC2. So our second cross-sectional area. And then if we make that, if we run that, it looks like we're good. So we need to look at our flow rate change over time. And so to do this, we know that our flow rate changes at a specific time, and we're given that in our problem statement. To do this, we're going to use a switch function because the initial flow rate changes at time 100 and time 200 seconds. So a switch function basically allows us to switch at partway through the problem, or it allows us to calculate, partway through our calculation to switch the time and look at the difference with an increased flow rate, right? So to do this, we need to define our switch function, which is the time, right? So you can tell where you are in the length of our experiment or the length of our problem. V1, V2, basically the flow rate at our first and second flow rate, and then the time of switch, so the time at which we are going to switch our two values here, our V1 and V2, and then the scale. And the scale is used for the sigmoid function, which we'll basically use at the end, because if you think about it in real life, if we really have these two tanks and you're pouring water in at one speed and then all of a sudden you dump water in, the flow coming out doesn't immediately change, and in fact it's a gradual increase of flow. If you start pouring more water in, it takes a while. The height will probably rise and then it will catch up. And as long as you're keeping your input the same, it should be a steady state eventually once it reaches that equilibrium. And we should be able to see this with our graphs, right? So let me make sure I've got those values right. And then now we return using our sigmoid function, which is off of the JAX library. So the JAX sigmoid function, and that is t minus t switch over the scale, and then t minus t switch over the scale times V2 minus V1, and then plus V1, and quick colon. Okay. So this is our switch function using a sigmoid function to kind of make that change gradual. And we see that in these functions, right? And so we use that immediately to determine our flow rate. Let me get another one just so I can lay it out. Oh, come on. It's Q1 in, right? And the reason I'm one sec. All right, it's this has to do with respect to time. Here we go. I just wanted to set them up so you could see what we're solving for. Basically, the input, the inlet flow rate in both tanks, right? So what's coming in from the top, and we know that changes at a certain time, and I'm about to show you how we use that. And I'll let you know what those times are and what happens at those times. So right now, we return our switch function. This dictates how our flow rate goes, so our time, right? Still, that's a ever-changing variable, so we never have to define time. So we have our time, we have our V1, which is our Q1 in initial, and then our second flow rate, it says it reduces by 80%. This is for tank 1 again. Reduces by 80%, or no, becomes 80%. Reduces to 80% of its original flow rate, which we know is just 0.8 times the original flow rate, which is our Q1 in initial. And then the time of the switch of that happens. So at 100 seconds, our T switch, our time of switch is at 100 seconds, and that basically the Q1 in initial becomes 80% of what it originally was. And our scale for now is just 1. Okay. And now our second one is basically the same thing. Switch function T. Now we have our Q2 in initial, and our second switch, which is for our inlet 2 and inlet to tank 2, is actually, it becomes 250%, right? 2.5 times the Q2 in initial. So a huge increase in our second tank, and this happens at 200 seconds. Scale, we're just going to leave as 1 again. Okay, I'm gonna run everything. Just so we can see how everything works together. And now we should be ready to look to solve solve this differential equation and start doing our graphs here. Okay, we need our time that we want our trial or our experiment to run for. And with this, we're basically just an endpoint, right? So if we start at a certain time, we know we have a switch at 100 and 200. Now we're looking for an endpoint here, right? So time end, T end, we'll set to, since we have one at 100 and 200, we can just go to like 500. Any point after there, as long as we see what ends up happening. Let me shift enter down through here. Okay. So yeah, 500 seconds will be more than enough to show how our graphs turn out. So now we're actually going to be using that solve IVP function to solve for a result. So solve IVP, and then so we're going to use our DH dt function. Need to get our time frame. I'm running out of water too. Better finish this quick. Our time frame is going to be 0 to t end, 0 to 500 seconds. Okay. Then we need our initial heights, which is h1 initial and H2 initial. And then we need a method for our solve. In this case, we're just using the Redal method, which is just the method we were told to use and specified. And then we have to set dense output equal to true. And shift enter. Okay. Now we can look at our cross-sectional area. Why isn't that calculated? Okay, I'm gonna type out the rest of this because we may need a few more lines to help make up for this. So now we're gonna basically solve for our time axis, our x-axis, right? T plot. So our time plot, which is just gonna be a linspace function, JNP linspace, and that we know our starting value is 0. Our ending value is T end, and the number of values here is going to be 501 because again, if you go from 1 to 500, but you're also including 0, it's 501 individual data points basically that we're going to put in here. And then our solve is equal to res.sol. And that's T plot. So cross-sectional area is not defined. I believe, okay, it can be defined as 1. Okay, so we're going to put in our cross-sectional area, AC1, make sure I have the correct AC1 and AC2. AC1 equals 1, AC2 equals 2. Let me run all. Okay. And now we're going to basically do our plots here. So we're going to set up a figure with subplots. So fig, make, subplots. And we want 2 subplots, so rows 1, so 1 row, 2 columns, 2 subplots. And we're going to add 4 traces, so fig, add trace. And they're all going to be scatter plots. So wait, fig add, doesn't look right. Trace. Go. And our go is our graph objects that we imported above. Polygraph objects is go. So go, one of those is a scatter plot, just as scatter. And then I'm actually gonna, just to make it simpler. Well, I'll lay it out first. So we need our x-axis, right, is equal to t plot, our time. our time as a linspace function, and then our y is equal to our sol 0. Um, okay, and then we can name it as, so we're graphing both our heights over time and our flow rates over time. So this can just be H1 as a name, H1. And we're going to put this in row 1 and column 1. So this will be part of the first plot here. Unexpected name equals H1. Add trace got an unexpected keyword. Name equals H1. Name equals H1. I'm confused as to where this is falling short. Name. Add trace got an unexpected keyword argument. So it's probably within this. I guess we don't need a name. Name. It's not letting me name. Name equals. It's confusing. If we take it out, it's at the end of the world. That's interesting. It's like, I can tell it's doing the right thing, but it's almost like inverse of what we're looking for. Anyway, we can kind of work on our other plots or other traces and maybe see if we can fix the issue. So yeah, our second one is the only thing we're changing is we're looking at our first value of h's, again in row 1, column 1. I'm confused as to why. Okay. It's just the parenthesis in the wrong place. So name equals h1. So this might work. Okay, we are getting the same awkward numbers here, or this awkward looking graph, which I'm not liking. But let's see if adding other traces will help. So if we add our 1 here, this is our h2, our second height. I believe that's the only difference in traces for our first plot, which is honestly not great, not looking good for how our it's going to be developed here. I'm wondering if I got something wrong in the sine function. That doesn't look like it. Sine function again. because it almost looks inverse, right, of what it should be. At time 100, we have a change. Time 200. So our switch function's working. It's got to be something super small. Okay, again, I'm gonna run through this again, or I'm gonna work on our second plot here before we go back and find out what went wrong there. So these two are going to be in column 2. Our names, we want our Q1 in, Q2 in, and our X is going to be our T plot again, and our Y is going to be they're going to be different. They're going to be Q1 in T plot, and this one is going to be Q2 in of our x-axis, our T plot. So these at least should work out. Let's check those. And that is looking exactly how we want it, actually, which is actually will help us locate our error. This is exactly what we're looking for, right? So if we have an Q1 in, and then at time 100, at 100 seconds, it's slowly, right? We get the sigmoid function. The sigmoid function actually kind of bumps it back, so it's not at this. It starts changing at like 93 seconds, 95 seconds here. It gradually becomes 80% of what it was, and this one becomes 250% of what it was, right, at time 200. And over here we see the heights. I'm wondering if these are actually accurate, because if we think about it, no, our height shouldn't increase both times. Let me, we can kind of pinpoint this area here. And is this where I did, where I copied over? That would be funny if I straight up copied over without, and I missed something there. Hmm. So our square root no, to me this looks good actually, unless our return function's wrong. But even that looks good to me. So I think at the end of the day we can see exactly what's going on. That our height slowly changes.